Are you going to focus? Right, and well, this is take 2. I thought I would just filming this, but never mind. Hello, and a warm welcome back. This is part 3 of the DIY valve tester, and we've already built, hopefully as you have seen in part 1 and 2, a valve regulated anode power supply for the reasons previously mentioned, in that it is more forgiving of high voltage transients and any overcurrent situations. We'll get into this sort of overcurrent stuff later on. Next I'm going to turn my attention to the bias supply. AC coming in, bridge rectifier, negative here, positive here. So we don't want anything really complicated. All we need is a big cap, reservoir cap, there, and I'm going to use a 1000 microfarad 63 volt, and then we just want a couple of series of CRC filters. Because that is positive, that's going to be tied to our ground of the valve tester, as it were. Eventually I will draw a proper schematic so you can copy me if you want. And then we just need a few CRC filters as mentioned. Resistor, we want the resistor on the bottom because we're upside down, you dig? Hold on. Don't really need two either, just one would do, but never mind. This is what I've got. Very simple. We work that out in a minute. I'll show you how to do that. So we've got 1000 here, 1000U, 470U, 470U. That will give us a really rock solid bias supply, more than adequate. And to vary the voltage, we're not going to use anything more complicated than a potentiometer. There we go. So that's the positive. That's going to be tied to our ground of our valve tester. This is a negative here, and we'll get variable negative out here. Let's go into some values. Right, after mucking about with power supplies, building them for the last 10 years, I have a rough rule of thumb. Whether it's correct or not, I do not know. And that is to use a value of 2k per volt. So as we've got about 50 volts coming off here, it's about 53 ish. I'm going to use a 100k pot. We want a linear pot because we don't want a logarithmic sort of scale. I mean, a log pot would do if that's all you got, but linear is better. And I have these really nice, I think these are Allen and Bradley. Well, maybe these aren't Allen and Bradley exactly, but they are high quality potentiometers that came off a Tektronix 500 series oscilloscope. That will do for that. In series with that though, what we'll do is use not this exact 10-turn pot, but we'll use this 10-turn pot in series. So they will go something like, let's make that a bit bigger so we can fit them all on. Well, let me just try and think about this. Right, I got my thinking head on there. Right, this will be something like 5k. And oh sorry, it's a bit of a crop K. And that will be strapped as a rheostat, if you're with me, something like that. That's a wiper there. Oh, I've made the right cock up of this schematic. Forget that bit there. And then that will go into our 100 100k pot, positive up here, and that's our bias voltage there. So we use the 100k pot, this one, to set like a rough, say, I don't know, 20 or 10 volts or whatever, and then we use the 5k pot to dial that in. Bish bash bosh, dead simple. Aha, one thing I forgot before I go and knock that up. We need to figure out the values of these resistors. Now then, I've fallen foul with this before. We've got that big 1000U here that will stomp on any AC ripple, and then we need to choose our resistors. This one particularly, well, both of them particularly, we don't want them to be too big, because otherwise these resistors, these capacitors here will take ages to charge. And so to find out what we want, the sort of value, you know, ish what we want, turn the computer, turn the calculator, rectifiers, computers, capacitors. It's very complicated. Where are we? 1 divided by brackets 2 times pi, which is 6.28, times by a capacitance, which in this case is 470U, so we've got to express that as farads. You can't fucking see, can you? Express that as farads, which is 0.00470, and then we times by that the frequency that we want to stomp on. Well, ideally we don't want any frequency, we don't want any AC component, so we could use 0, but let's just use 1 just for the crack. 1 equals, and that will give us a value of 338 point whatever ohms. So we want something like, I think, and this I'm just going in on experience and I'm riffing here, something like 150 odd there and a 330 odd there, and then that should give us a really ripple free DC bias voltage that is rock solid, ain't going to be jumping up and down a bit, ain't going to be affected by ripple, in other words. Okay, hope I haven't gone too fast for you, but a lot of electronics, something simple like this is very, very simple. You can just do it in your sleep. That's the PCB, in inverted commas, knocked up. Just use the old faux Dremel Minicraft drill, bit of copper clad board, bish bash bosh, a few drills and all that. So next I just got to populate it and then bung it in the chassis and whatnot, and then that's the bias supply done. I think I've done some videos about this method of doing boards. Most of it will be like, ooh, shite, throughout type sort of thing. Oh, pardon me. Where do you call it? Bridge rectifier there. The resistors will go on the back. Oh, shite. The resistors will go on the back. Says piss in the back with CAD or whatever, and ordering boards from China. Love the Chinese, don't like Xi Jinping and his attitude towards the world. So any sort of commerce I won't chuck in their way. Maybe we'll bring down the regime one day. The bias circuit is built on the board, same as last time with the other power supply. We've got a potentiometer holding the device. It's a 100k linear potentiometer. Sorry about the creak. Ah, fucking glare. Right, you can see that. So I'm going to switch this on. It's just loosely wired in for the moment to the transformer. As you can see, that's reading minus 36 volts. Now it's reading 0 volts. Let me try setting it to like a typical voltage for an ECC 83 or 12AX7, which is 1.5. It's a little bit tricky, you see. Let me whack it the other way. 57.9, 60 volts. So we can go from 0 to 60 volts. Right, let's try adding a 5k potentiometer as illustrated earlier on with my rough schematic. Right, I've been tried a 5k, which was a bit silly of me because I ignored my 2k resolution. I've got a 2k, so I've set the big pot to roughly 1.5 volts. And there we go, 1.5 volts. Pretty much bang on. Yeah, I know it's floating about, but that won't make a great deal of difference when testing a valve. Bias supply is built, that will go in there. Pop. Next, heater supply. So that's the proposed schematic for the heater supply. A few bits and bobs missing off there, but that's the major components. So we start off with a winding from the power transformer, goes into a bridge rectifier. As you can see, I've drawn a load of capacitors that is basically strapped across each diode of the bridge rectifier. We'll get onto those in a minute. The main reservoir capacitor wants to be something like about 3000 U. Again, my sort of rule of thumb is you would want about 1000 microfarads, 1000 U per amp. As this is about a 3 amp power supply, then something like a 3000, 4700, something like that. It just depends what we've got in the old box. That goes into a LM317 variable valve regulator. I don't know what this one is. I usually use LM317 AHV. I'm going to reuse this one, which is probably off an old power supply. Get back to that in a minute. We've got the usual resistor there from output to adjust, 5k pot to adjust the voltage, and then basically what that does, the output of the LM317 through a couple of 10 ohm resistors goes to either some tip 3055 or some 2N 3055. More about that in a second. And then to share the sort of current, as it were, we've got a couple of 0.1 ohm resistors on the emitters. Bop, 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 bop. And that's about it really. The other thing that is usually done with LM317s is you have like a couple of capacitors either on the input or from the adjuster ground, etc. And that's mainly to prevent oscillation. I've never really had a problem with that in the past, but we could do that if we wanted. See the LM317 datasheet. Also, there's no protection diode, so usually you'd have a reversed bias diode across the LM317, maybe one going to the bases of the series pass output transistors. We'll see. We'll keep it loose at the moment. Remember those capacitors across this bridge rectifier, across each diode? The reason being is that diodes, some diodes, depending on their specification, are a bit slow switching. So I hope you can see that. We've got on the output of the bias power supply, we've got these glitches here. Let's slow the time base down. I'm quite sure. I've got it on 10 times magnification, so you're talking only, woo, right, okay, so let's put some figures on this. We're on, right, 5 millivolts per division. So these spikes are 5 millivolts peak to peak ish, maybe a little bit more. If we was to look at it on a different scope, maybe we could like zoom in on them and everything, but I think that illustrates the purpose. So just to confuse the issue even more, I've turned the power supply off and I've discharged the capacitors. We now have an output of bugger all. All I'm doing is adjusting that pot, and as you can see, that high frequency crap is still there. So is it an artifact of the test setup, or is it like a product of the oscilloscope? Good question. So let's have a sniff about. What I'm going to do, I've got the oscilloscope probe off the test gear, and I'm just going to move it about around the PCB. So that is just touching, oh no, one moment, that is just touching the PCB. There's no power applied at all. I'm just going to knock the resolution of the gain down of the thing. So that is me just touching the circuit board. I'll spin you around so you can see. That's all I was doing. And we've got a big trace on the scope, lots of peaks, lots of crazy sort of, it's a very complex waveform, but there's no power on that at all. So you have to be careful sometimes in what it is that you're seeing, what it is that you're detecting on a circuit. And so with that in mind, I'm glad I checked that. I'm not going to bother with those capacitors after all. And to be honest, this isn't a really high gain amplifier like a phono amplifier or something like that where noise is really an issue, so it doesn't bloody matter. So in that case I won't bother with the capacitors on the heater supply either. Well, that's the heatsink cutting off, fettled, standoffs on there. I've got another standoff and the gubbins to secure just 1 point at the bottom rather than 2, because of like things in the way inside the chassis, so can't really get to do nuts etc. I've mounted the two 2N305s on the heatsink. They should be isolated from this heatsink, because this heatsink through those standoffs will go to the chassis. The chassis will be mains earth referenced and ground referenced, so the collectors of these transistors cannot. So the transistors should be floating as regards the metal of this heatsink. So I'm just touching one probe on there, got me meter set to continuity. One is okay, however the other one isn't, so I need to try and sort that out. tricky blighter, this one, to find out what's happening. So continuity, I've got that down tight. It has to be tight. I haven't got the little connector on there, so I'm just going to relieve a bit of pressure. It has to be tight because it's got to make a good connection to the collector. I've just released a bit of tension there on the screw. Oh ho! That leads me to believe that the sill pad is at fault. We're okay until we screw it down tight. Let's have a look. It shouldn't be. The bloody fresh sill pads, and I had to sort of scrap a couple of nice mica washers because they're old and cracked and all the rest of it, and I didn't want any shorts. So let's investigate. Get the other bugger off. It's probably like a bit of grit or something, I don't know. Something's amiss anyway. What we got there? Aha! I don't know if you can see there. Bit odd with the sill pad reflecting. There's a bit of sort of grit there, look. So my suspicions are confirmed. I did try to clean all these up yesterday, but this one's okay, so I'm gonna fettle that a bit more, try to smooth the surface up a bit better, and try again. Well, that's sorted now. No continuity. However, that's given me a bit of thought about the mounting of this one. I wasn't able to clean the surface up of the heatsink to the degree that I would have liked to have done, because there's all these like sort of little protuberances here. So I'm going to go and put some heat gunk shit on there, and that should hopefully give it a better surface to dissipate heat from, if you with me. There's a little bit of the gunk on there, and unlike a lot of YouTube techs, I'm not really scared of the stuff. Yeah, just whack it on with a finger. No special applicators or anything. I mean, compared to some of the shit I've seen in life, this is nothing really. When you've mucked out like a chicken shed where the chickens have been been in there for bleeding years, and you know, several layers, and the chickens are nearly up to the bleeding roof. Yeah, a bit of gunk like that holds no fear for me. It's only a bit of white gunk, for fuck's sake. Jesus. So they're all mounted. Let's test it for shorts. No. Yes, obviously, because that's going through the heatsink doodah thingy. Metal. No, obviously don't do that. Emitter base emitter, whichever. No, everything is groovy, as Simon and Mr. Garfunkel said. So next we just got to wire that up. We've got to wire the emitter resistors and the base resistors up on these handy dandy little protuberances here. I can't remember what they're fucking called, so yeah. Sometime later, there's all the two N3055s mounted with the emitter resistors and the base resistors. So, and the two collectors are joined together. So now all I have to do is join that. You're gonna creak. Of course you are. To the big reservoir capacitor here. As you can see, it's all plumbed in. We've got the AC from the transformer, bibbidi bobbidi bobbidi, going to the bridge rectifier, bibbidi bobbidi bibbidi bobbidi, up to the big reservoir cap. 470k resistor across the negative and positive of these of this big cap. The two 5000 mic capacitors are connected together in parallel, so we get 10,000 mic at 40 volts. Now we just need to take some wires out of there to the heatsink with the series pass resistors. That's everything wired up, all the transistors, resistors and whatnot. Next I've got to just fix the heatsink in, wire it all up. Before I did that, I just went over all my joints with a magnifying glass to check for cold joints. You know what a cold joint is by the colour of it. If it's like a sort of dull silver, then you know you've got a cold joint. It might do, it probably will do, but nah. So I went over all of them with some good solder, applied a bit more heat and everything, and I'm a lot happy with the result. I'm not happy with some of the dressing and everything, but I know that the joints are good. And to test the buggers, come in from a different angle, give them a fucking good tug, give it a good old poke and everything, because the last thing I want to do, having spent all this frigging time fettling the thing and choosing this, that and the other and everything, is to put the thing in and then find out that we've got iffy joints, and to absolutely 100% make bloody sure. I'm going to give it a continuity test to the heatsink. Sorry, I'm trying to think what the fuck I'm doing here. No. So the collectors are okay. Everything's cushy. I've cut the traces on the board that need cutting, and really there's only, at this point in time, one component to go on here, apart from the LM317, which I've got mounted on a little heatsink, but it doesn't need anything substantial, because the two 2N3055 series pass transistors will do all the current heavy lifting, so there'll be very little current. All that will be coming on the out of the sort of output, as it were, is like the base current, which is, yeah, I don't know, 1 millivolt tops, 1 milliamp tops. So I'm just about to put the resistor on there that goes from the output to adjust, and then all we need then is a 5k 1010 pot to go from ground to adjust. Anyway, I just thought I'd give you a little tip. So this is obviously a high precision pot, but when you're mounting components on like a circuit board and things, it's a good idea to mount them in such a way that you can see the value of the component, be it a capacitor or transistor or whatever, so that if anybody or yourself comes back later to have a look at the circuit to try and diagnose a fault or whatever, or just to understand the circuit, then they can see the value of the component and hopefully work out what the hell is going off. So just going to finish, oops, again it's hard working around the soldering camera, bending that round there so that looks nice. Not quite got that quite right. So if I mount it like that, I don't know if you can see the 238R is visible, and then it's just a matter of bending the legs at about, I'm still recording, sorry, it's just camera's doing weird things. It's about 90 degrees, and we'll cut those off. It always amazes me that resistors, I mean, these legs are what, about a mil, nearly getting on for, well, maybe half a mil thick, and it always amazes me how strong they are attached to the actual resistor inside. It's yeah, it's an amazing feat of engineering. I mean, I could probably tug on that and give it, you know, a right good pull, like, and everything, put a lot of force on that, but yeah, amazing. Anyway, I digress. So I'm gonna solder that in there. As mentioned, it's got to go from output to adjust, and because like I'm working on my own a lot of the time, obviously I ain't got nobody to hold the component, so I'll just put a blob there to give me a rough idea of where things go, and then another blob about there. I'll just put a little bit more. Oops, usually take a bit more care than that. Get the solder set up. I see a lot of people like tear off or, you know, cut a length of solder and then use that to solder things. I prefer it on a reel because like it's just there, and then I can just tin the lead there. Oops, so right, just got to mount that so that we can see the value. Tack it in. Now I can solder that properly, although that's really a good joint. On this end, and then what I'll do, a bit more heat, just make sure the component is properly seated, and then now I just need to connect this with a couple of flying leads to the, so now all I need to do is just get a few flying leads coming off here from ground to adjust to this 5k pot, and then the only other connection really, apart from the DC feed as it were, is one connection to the series pass transistors, which goes to the base, which is here. I've mounted the big heatsink on the back of the valve tester chassis. There's the two RCA 2N3055s. All the resistors and everything, as you know, are on the back there. That ain't going nowhere. I'd have liked to have probably done like a little bit better job, but it's okay. You know, probably sprayed that black and all the rest of it, but it is functional. To keep the leads that goes to the front panel neat, I'm just going to twist them with just a cordless, and I've just got a bit of copper wire twisted there. That goes in there. And it's just a matter of, so we've got the leads there. put them through there. I'm just going to tie them off camera. As you can see, I've got one end sort of clamped to the bench. I hope you can see. If you just start that up, it will just not do a very good job. So you've got to get your fingers there. Don't go too mad, and then just work your way along. And there we go, nice twisted pair of wires. This is also good if you haven't got any screen cable. This sort of twisted pair like that is almost as good as a screen cable for signals. Come on, focus, you fucker. Because the LM317 adjusts part of the circuit, doesn't carry a lot of current, we don't need anything really thick. I think it's something like, I think the reference current is something like 125 microamps. Oops, again, please allow my clumsiness. It's due to having the fucking camera in the way. But at the moment I'm not going to connect that up to everything, because when you've just constructed a circuit, even though you've checked it out and all the rest of it, it's a good idea to proceed with caution. So it's a good idea, once you've disentangled your leads from all the other leads and wires and everything, is to take a resistance reading on the input to make sure that we haven't got a direct short. And I've got to be careful here, because if I use my finger there to keep that wire in place, it will read the resistance across my body. So we have to keep one end floating. Well, as you can see from the meter, we've not got any direct short, so still proceeding with caution. I shall connect the ground to my current limited power supply. The current limited power supply is worth its weight in gold. And then I have a 3K9 power resistor as a load, because when you're testing a voltage regulated you know, like a LM317 regulator power supply, or any regulated power supply, it's always a good idea to have a load. You get a better reading. So I'm going to connect that up to all my meters and whatnot, and then we'll power it up with the current limited power supply. So this meter is across the power resistor that we're using as a load, 3K9 as mentioned before. I've got the current limited power supply set to 10 volts at the moment. Just put the output on, no red lights. I'll increase the voltage to about 20 volts. I can't remember exactly what the output of the bridge rectifier, transformer, etc. is, but I am adjusting the potentiometer and that seems to be working. I'll just give it, so the power supply is set to 25 volts. Not sure if that's about right, but it will serve for now. So here's a potentiometer, 5k potentiometer holding the vise. It won't read 0 volts, but we don't want it to read 0 volts. You can get a LM317 power supply to read 0 volts, but we don't need to in this case. So we've got no magic smoke escaping, nothing untoward. So we've got 25, less than 25 volts going in, 20 volts coming out. That's good. So that's with a very light load. Let's give it a bit of a heavier test by using a lower resistance as the load. I've got a 10 ohm power resistor. Don't want to leave it on there too long. That's the reading there. Just knock it down to sort of typical 6.3 volts for something like a ECC whatever. And as you can see, that's pretty bang on. It's gonna get toasty. So everything seems to be working with the current limited power supply. Let's connect it up to the transformer and give it a proper test. The heater power supply is connected up to the transformer. As a load, I've got a 5 ohm resistor which is getting warm. Just feeling at the back here the two 2N3055s. They're moderately warm, so that's good. And that's our voltage there. Right, well that's an acceptable reading for testing valves. It's out by what, 10 millivolts, which is higher which is either here or there. So with that, I'm going to continue onwards and upwards. In the next episode we are going to get into the old screen supply, current limiting, and some other juicy goodness. A lady called Susie kindly sent me over a schematic and everything of a power supply that she's had good results with. We'll compare and contrast and get into a bit more juicy details. Thank you very much for watching. Take care of yourselves. Ta-ra for now.